so. I've drawn the wrong way for what I'm used to thinking about it. No, I had it right. This way, there's another notch, and a sawtooth wheel like this with sharp up notches and relatively slow down notches all the way around. And then, this is a wheel on a shaft. And then on this thing, there's a little piece of pawl, a thing called a pawl, which is on a pivot here, and which is held down by a spring. It gets in the way of the wheel, but that's small technical difficulty. It's just two-dimensional, and actually it's set a little bit below. Now, this wheel can only turn one way. If you try to turn it this way, then these straight-edge part of the teeth get jammed against the pawl, and it doesn't go. Whereas if you turn it the other way, it just goes right over the finger, snap, snap, pop, 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 pop. This they use them in clocks, so when you wind watches, they have this kind of a thing inside so that you only can wind it one way. And after you wound it, it holds a spring. And now we want to discuss, you see, it's completely irreversible in the sense that the wheel can only turn one way. Now this irreversible machine, this wheel that can only turn one way, has been imagined that we could use it for a very useful thing, say a very interesting thing. Because of molecular irregularities, because of molecular motion, perpetual motion, there's a perpetual motion of molecules, and if you build a very delicate instrument, it'll always jiggle because it's being bombarded irregularly by the air molecules in the neighborhood. So that's very clever. We'll connect this with a shaft, which is hard to illustrate in 3 dimensions. It goes way out here. We connect this to it with a shaft, with a vane, with a wheel that has 4 vanes. Actually, my angles of things have gotten a little bit mixed up. Look down on the shaft. This thing's got 4 vanes like this. And those are bombarded. They're in a box of gas here. And they're bombarded all the time by the molecules irregularly. So the thing is pushed sometimes one way, sometimes the other way. But when it's pushed one way, this thing gets jammed. But when it's pushed the other way, it goes around. So we find the wheel perpetually going around, and we have a kind of perpetual motion. That's because this wheel is irreversible. But actually, we have to look into the details. The way this works is that when the wheel goes one way, it lifts the pawl up, and then the pawl snaps down against the next tooth. And it will bounce. If it's perfectly elastic, it'll go bounce, 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 bounce all the time, and the wheel can just go down around the other way when the pawl accidentally bounces up. So this will not work unless it's true that when the pawl comes down, it sticks, or stops, or bounces and cuts out. If it bounces and cuts out, there must be what we call damping or friction again. And then the falling down and bouncing and stopping, which is the only way this will work one way. Heat is generated by the friction. So this part of the wheel over here will get hotter and hotter. But however, when it begins to get quite warm, something else happens. Just as there's Brownian motion or irregular motions in the gas here, so whatever this is made out of, the parts that this is made out of are getting hotter and are becoming more irregular. So a time comes when this is hot enough that the pawl is simply jiggling because of the molecular motions of the things on the inside. And so it bounces up and down on here because of molecular motion, the same thing that was making this vane turn around. And in bouncing up and down on here, it is up as much as it is down. And when it is up as much as it is down, a tooth can go either way. As a matter of fact, the thing will be driven backwards. If this one was hot and this one was cold, the wheel that you thought would go only one way will go the other way. Because in the terrible bouncing up and down of this wheel, every time it comes down on an inclined plane. And so pushes the wheel this way. Then it bounces up again, comes down on another inclined plane, and so on. And so if this side is hotter than this side, it'll go around this way. What's it got to do with the temperature of this side? Suppose I didn't have that at all. Oh. Then, if it's pushed forward by falling on an inclined plane, the next thing that will happen is it'll bounce against that tooth, and the wheel will bounce back. But in order to prevent the wheel from bouncing back, we put a damper on it and put vanes in the air so it can't go back. And then it will go one way, but the wrong way. And so it turns out that no matter how you design it, a wheel like this will go the one way if this side is hotter, and go the other way if this side is hotter. But after there's a heat exchange between the two and everything is calmed down, it will neither go one way or the other. And so that's the technical way in which the phenomena of nature will go one way as long as they're out of equilibrium, as long as one side is quieter than the other, or one side is bluer than the other. The conservation of energy would think would let us think that we have as much energy as we want. Nature never loses or gains energy. Yet the energy of the sea, for example, the thermal motion of all the atoms in the sea, is practically unavailable to us. In order to get that energy organized, herded, used, make it useful, make it available for use, we have to have some place that's at a different temperature. We have to use a difference in temperature, or else we'll find that although the energy is there, we cannot make use of it. There's a great difference between energy and availability of energy. The energy of the sea, for example, is a large amount, but it's not available to us. I think I can give an analogy to give some idea of what the difficulty is this way. The conservation of energy means that the total energy in the world is kept the same. But in the irregular jigglings, that energy can be spread about so uniformly that there's no, in certain circumstances, that there's no way to make more go one way than the other. There's no way to control it anymore. I don't know if you've ever had this experience, but I have had going to the beach with many towels and so on, and sitting happily on the beach and having a tremendous downpour suddenly come, picking up the towels as quickly as you can and running into the bathhouse. Then you start to dry yourself, and you find that this towel's a little wet, but it's drier than you are. And you keep drying this one, then you find that one's too wet. It's wetting you as much as it's drying you, and you try another one, and pretty soon you discover a horrible thing. All the towels are damp, and so are you. And then you keep picking them up and putting them down and rearranging them, and there's no way to get any drier, no matter how many towels, even though you have many towels. Because there's no difference, in some sense, between the wetness of the towel and the wetness of yourself. I could invent a kind of a quantity which I could call ease of removing water, or, let's call it the ease of removing water. The towel has the same ease of removing water from it as you have. And so when you touch the towel to you, as much water comes off of you from the towel to you as it goes from you to the towel. It doesn't mean there's the same amount of water in the towel as there is on you. A big towel will have more water in it than a little towel, but they have the same dampness. So when things get to the same dampness, then there's nothing you can do any longer. Now, the water is like the energy because the total amount of water isn't changing. But if we had a world which was limited, you see, if the bathhouse door is open and you can run into the sun and get dried out, or find another towel, you see, okay, that's different. Then you got saved. But if you have everything closed and you can't get away from these towels, you can't get any new towels. So if you imagine a part of the world that was closed, wait long enough, and in the accidents of the world, the energy, like the water, will be distributed all over all of the parts evenly. And there's nothing left of one-wayness. There's nothing left of the real interest of the world as we experience it. Thus, in this situation here, which is a limited one, in which nothing else is supposed to be involved, the temperatures gradually become equal on both sides, and the wheels doesn't go around either one way or the other. And in the same way, this situation is that there is, if you leave a system long enough, it gets the energy thoroughly mixed up in it, and no more energy is really available to do anything. Incidentally, the thing that corresponds to the dampness is called the temperature. And although when I say two things with the same temperature, when things get balanced, it doesn't mean they have the same energy in them. It just means it's just as easy to pick energy off of one as to pick it off the other. So if you put them next to each other, nothing apparently happens. They pass energy back and forth equally. The net result is nothing. So when things have become all at the same temperature, then there's no more energy available to do anything. And the principle of irreversibility is that if things are at a different temperature and are left to themselves, as time goes on, they become more and more at the same temperature. And that the availability of energy is perpetually decreasing. This is another name for what's called the entropy law, which says entropy is always increasing. But never mind the words. To state it the other way, the availability of energy is always decreasing. And that's a characteristic of the world in the sense that it's due to the chaos of molecular irregular motions. Things of different temperature left to themselves tend to become of the same temperature, but a piece of, if you have two things at the same temperature, like water on an ordinary stove without a fire, the water isn't going to freeze and the stove get hot. But if you have a hot stove with ice, it goes the other way. So the one-wayedness is always to the loss of the availability of energy. Well, that's all I want to say on the subject, but I want to make a few remarks about some characteristics. Here we have an example in which an obvious effect, the irreversibility, is not an obvious consequence of the laws, but that the effect is rather far from the basic laws. It takes a lot of analysis to understand why this effect, and that the effect is of first importance in the economy of the world, in the real behavior of the world, in all obvious things, that my memory, my characteristics, the difference between past and future are completely involved in this, and yet the understanding of it is not prima facie available by knowing about the laws. It takes a lot of analysis. It is often this way, that the laws of physics are different, or the laws of physics do not have a direct relevance, obvious relevance to the experience, but that the laws are abstract from the experience to varying degrees. In this particular case, the fact that the laws are reversible, although the phenomena are not, is an example. There are often great distances between the detail laws, and the main aspects of real phenomena. For example, it's something of this kind, that if you watch a glacier from a distance and you see the big rocks falling into the sea and the way the ice moves and so forth and so on, it isn't really essential to remember that it's made out of little hexagonal ice crystals, that the ice crystals are hexagonal. And yet, the character of the little hexagonal ice crystals, if understood well enough, is in fact the consequence of this is in fact the motion of the glacier. But it takes quite a while to understand. In fact, nobody knows enough about ice to, no matter how much they study the crystal yet, to really understand all the behavior of the glacier. But the hope is that if we do understand the ice crystal, we'll ultimately understand the glacier. But there's a large, in fact, although we've been talking in these lectures about the fundamentals of the physical laws, I must say immediately that one does not, by knowing all the fundamental laws as we know them today, immediately obtain an understanding of anything much. It takes a while, and even then it's only partial. Nature, as a matter of fact, seems to be so designed that the most important things in real world seem to be a kind of complicated accidental result of a lot of laws. To give an example, nuclei, which involve several nuclear particles, protons and neutrons, are very complicated. They have what we call energy levels. They can sit in states or conditions of different energy values. And various nuclei have various energy levels. And it's a complicated mathematical problem, which we only can partly solve, to find the position of the energy levels. Now, it's not, you can understand that it's complicated, and therefore there's no particular mystery about the fact that nitrogen with 15 particles inside happens to have a level at 2.4 million volts, and that and another level at 7.1, and so on. And the exact position of the levels is obviously a consequence of an enormous complexity. But the remarkable thing about nature is that the whole universe in its character depends upon precisely the position of one particular level in one particular nucleus. In the carbon-12 nucleus, there's a level at 7.82 million volts, it so happens. And that makes all the difference in the world. The situation is the following, that if we start with hydrogen, and it appears that in the beginning or in the earliest times, the world was practically all hydrogen. Then, as the hydrogen comes together under gravity and gets hotter, nuclear reactions can take place and it can form helium. And then the helium can combine only partially with the hydrogen and produce a few more elements, a little heavier, but they disintegrate right away back into helium. So that it was for a while a great mystery about where all the other elements in the world came from, because starting with hydrogen, the cooking processes inside the stars would not make much more than helium and a few others, half a dozen other, less, as a matter of fact, other elements. And faced with this problem, Professor Hoyle said that there is one way out. I think saltpeter also, he's here, so I have to be very careful. If 3 helium atoms could come together to form carbon, We could easily calculate how often that should happen in the star, and it turned out it should never happen much, except for one possible accident. If there happened to be an energy level at 7.82 million volts in carbon, then the 3 helium atoms would come together, would stay a little longer than they ought to, on the average, if there were no level there, before they come apart. And staying there a little longer, there's enough time for something else to happen and to make other elements. And if there was a level of 7.82 million volts in carbon, then we could understand where all the other elements in the periodic table come from. And so, by a backhanded, upside-down argument, was predicted that there is in carbon a level at 7.82 million volts, and then experiments in the laboratory with carbon show indeed that there is. And therefore, the existence in the world of all these other elements is very closely related to the fact that there is this particular level in carbon. But the position of this particular level in carbon seems to us, after knowing the physical laws, to be a very complicated accident of 12 complicated particles interacting. So I wish to illustrate by this example that an understanding of the physical laws doesn't give you an understanding in a sense of understanding significance of the world in any way. The details of real experience are very far often from the fundamental laws. There are, in a way of speaking, in the world, we have a way of discussing the world which you could call, we discuss it at various hierarchies or levels. Now, I don't mean to be very precise, there's a level, there's another level, and another level, but I will indicate by describing a set of ideas to you, just one after the other, what I mean by hierarchies of ideas. For example, at one end, we have the fundamental laws of physics. Then we invent other terms for concepts which are approximate, who have, we believe, the ultimate explanation in terms of the fundamental laws. For instance, heat. Heat is supposed to be the jiggling, and it's just a word for a hot thing, is just a word for a mass of atoms which are jiggling. For that, fundamentally, we should think of the atoms jiggling. But for a while, if we're talking about heat, we sometimes forget about the atoms jiggling. Just like when we talk about the glacier, we don't always think of the hexagonal ice snowflakes which originally fell. Another example of the same thing is a salt crystal. Looked at fundamentally, it's a lot of protons, neutrons, and electrons. But we have this concept, salt crystal, which carries a whole pattern already of fundamental interactions, or idea like pressure. Now, if we go higher up from this, in another level, we have properties of substances like refractive index, how light is bent when it goes through something, or surface tension, the fact that the water tends to pull itself together, is described by a number. I remind you that we have to go through several laws down to find out that it's the pull of the atoms and so on, but we still say surface tension, and don't worry when we're discussing surface tension of the inner workings, always. Sometimes we do, sometimes we don't. Go on, up in the hierarchy. With the water we have the waves, and we have a thing like a storm. We have a word for storm, which represents an enormous mass of phenomena. Or sunspot, or star, which is an accumulation of things. And it's not worthwhile always to think of it way back. In fact, we can't, because the higher up we go, we have too many steps in between, each one of which is a little weak, and we haven't thought them all through yet. And we go up in this hierarchy of complexity, we get to things like frog, or nerve impulse, which you see is an enormously complicated thing in the physical world, involving an organization of matter in a very elaborate complexity. And then we go on, we come to things, words, and concepts like man, and history, or political expediency, and so forth, which is a series of concepts that we use to understand things at an ever higher level. And going on, we come to things like evil, and beauty, and hope. Now, which end is nearer to the ultimate creator, or the ultimate? So if I make a religious metaphor, which end is nearer to God? Beauty and hope, or the fundamental laws? I think that the right way, of course, is to say that the whole structural interconnections of the thing is the thing that we have to look at, and that the sequence of hierarchy, that all the sciences and all the efforts, not just the sciences, but all the efforts of intellectual kind, are to see the connections of the hierarchies is to connect beauty to history, is to connect history to man's psychology, the man's psychology to the working of the brain to the neural impulse to the chemistry, and so forth, up and down, both ways. And today we cannot, and there's no use making believe we can, draw carefully a line all the way from one end of this thing to the other. In fact, we've just begun to see that there is this relative hierarchy. And so I don't think either end is nearer to God's. And it's to stand at either end and to walk out off the end of the pier only, hoping out in that direction is the complete understanding, is a mistake. And to stand with evil and beauty and hope, or to stand with the fundamental laws, hoping that way to get a deep understanding of the whole world, with that aspect alone, is a mistake. And it is not sensible either for the ones who specialize at one end and the ones who specialize at the other end to have such disregard for each other. They don't actually, but the people say they do. But that actually the great mass of workers in between, connecting one step to another, are improving all the time our understanding of the world, both from working at the ends and working in the middle. And in that way, we are gradually understanding this connection, this tremendous world of interconnecting hierarchies. Thank you.